Lovely people. L, I circled it in the previous video. L is our trigger. L is our failing first member, our collapsing structure towards there. So there's K, there's L. I've already established in the previous video that M was part of this structure. As L buckles, it pulls on K and M, the floor slabs being interactive. It pulls on it. Why at this level does it seem like it more drops down? Well, it pulls, and these are unsupported. This span is able to hold itself, I think, for a moment before the span is too great, and then it buckles between the slab there, and it drops all down in one shot. So it has some redundancy until right about there, and then it buckles in one shot. Let's see that. Nope, wrong one. And right here. So this is L right here. Here's our L, this is our M, and that's our K. That's our wall for our privacy wall for the decorative wall. But it is a block column that goes up through the structure, and it's divided by it divides the rooms with drywall and studs or whatever it may be. Tom nailed it on the first shot when I tried to play stupid on it. Tom nailed it before I could probably finish my sentence. He nailed it on there. So shout out to Tom for my Columbo move being called out like instantly. That was awesome. It's not a solid block wall. I don't think all the way through. I think it's a wooden wall from what the way it configures. I'll show you in the drawing in a minute. Maybe I'll show you now. I don't think I can because I think I have this ready. Right. So let's do this. Let's do the overlay of this again. Let's pull that away for a second. So this is L, and let's go ahead and frame it. So this is L. Keep track of L. And at some point you're going to see it, the shape of the building. There's the roof, and there's the torque, the twist, the rotation. As L is dropping down, it's pulling on M. And at this level, K is pretty strong still. Yeah, this is K, and I's back there. So it's pretty strong still. And I have a reaction that will explain part of why it tears apart at the roof line, why it pulls the hooks out, and also that triangle shape detail. But that's not in this video. So you can see the L's pretty buckled. This is that decorative block wall system now buckling at this floor, ejecting some block. All right, so you see the shape. There's L. K is still present. It's pulling on M. Is now pulling on N also, causing it to torque. Let's go back. So again, look at the structure. This is L. So it consolidates towards L. L making the span, and there's your roof line, your rotation there. That's the parapet wall that we see here, and you see two floors of it. So you see this is the penthouse floor still intact. As you can see the gap between it. Let's see if I can get that right. Oh, no, that's right. I think I called the penthouse floor crushed already. I think the penthouse floor already dropped down to the penthouse floor dropped down to the 12th floor. I think at this point, I think my ripping is already happening here. Over here at the far end, it's already pulled off, and it dropped to the 12th, and then that load. So when it ripples up, When it ripples up, it's only I wanted to do a video to talk to you about bolt engagements, how bolts, all right, rebar and concrete are a bolt and nut. All right, the concrete's the nut and the rebar is the bolt. The bolt and rebar bolt and nut connection are at 3,000 psi up to 4,000 psi up here, above the 7th floor. I'll get to that. Above the 7th floor on these columns here, the bolted connection is only on 3 sides on the face here, and because there's nothing out in front, right? So it's only on 3 sides, yet it's a 20-foot span. I'm going to show you that. And so the critical shear area is only three-sided, but yet they still put 20 foot on it. It's interesting. I'll get to that. Hopefully I'll get to it real quickly in this video. I won't get interfered with the phone call I'm waiting for. All right, so there's your L. Your L is dropping down. Now, where is my video on? This is the New York Times video I did, and right now it's titled Champlain Towers Collapse Reaction Video, New York Times. They take, this is K, L, and M. They take more than liberty. They, this is an architect that's supposed to have drawn this, and she did not. This doesn't exist. This cross member here doesn't exist, nor does this one. It does not exist. So I want you to do this. I want you to think about that. It doesn't exist. So let's go with right, shapes. Nope, pencil. So this exists. Oh, the wrong one, this one. So this exists. Now I'm going to take some, go back and come across. You know what? I'll do that. So that exists. These do not exist. These are not existing, right? So X, X, X. They don't exist. This is open. So if that's open, oh, I think I can do this. I think I can do this. I think I can go like this and then this. Time to put up with it. So this is the true path. The walls, it goes around through the BMAs, back to that one a little bit. That's L, and then around to here, and then back to the structure. This is M. This is the structure that stayed. This is the shear wall system right here on this plane right here. On that plane right there. M stays. We showed that in the video. So that means this structure here, this is the structure that initially collapses, the roof plane. I showed just now in the video that L, this is L, is the one that everything's leaning towards. So L's are failing column. Okay, L's are failing column that causes the buckling of all the floors that come towards that direction. This again, this is the load path of the structure. This is why it's two different structures. This had a bridge here, which was an easy shear plane, if you will, right here, because as this came down, as this deck area came down here, it took out these guys, right? It took out the BMAs. It took out the BMAs and rattled I and K, and L ultimately buckled. And we see the planar boxes here. So the planar boxes are set down evenly. So this planar box is out here. So planar box is, oh, let me write in it. Yeah, planar box is out here. Planar box. Planar box is there, and it's set down. It's set down just a little bit, but pretty much plumb, right? It's set down a little bit. When it did that, it pulled on to do that, to get it to go down. That means it's pulling on this. Let me do a circle here. Let me change the color. It's pulling on this part of the, right there. It's pulling on that part of the BMA. So this part right there gets pulled on. Wrong one. It drops down. When it drops down, it pulls on this part of the BMA. I mean this beam, number L. The planer box goes down just a little bit. It rattles the L all the way up. Now let's talk about the engagement, the bolt, the connection. So I have to go here. So here's our L, and thereabouts. So this would be that when we see it tilt over. Let's look at that video again. We have our 8th floor, 9th floor. The shaking, the connections get lost. They lose their connections. Let's get to that. So I'll get rid of this one, and I come over to. Okay, it's here about that. I guess I'll give it away now. Is that our reinforcement on our basement framing is similar to the reinforcement on the first floor framing. The wires, you can see 14 fours, 14 fours. The exceptions are this does have a planer box on it. It does have isolated loading and a planer box across here. That's the exception of that, one of the exceptions, or some of the exceptions. Now, to this KLM, L is our failing one. As you can see, as I show you from the top view, that the load path is of such. Okay, so I think it's already open. So the load path is like this. I can move this all together. So if we have, we already know we have bad core samples here, right? Bad core samples. So we don't really have engagement there to be able to pull this down. Remember I said we can't have our cake and eat it too. And I did that in the reaction video saying that, hey, you can't tell me to pull down M if you're also telling me the deck is crap. So it pulls down the deck on its own. And that's what we get, the deck. Visually, we see the deck collapsed from here, just part of what we can see. So it's here, it's here. You know, how much of it's inside, I don't know, because I saw it presents like a little bit of concrete there, but nevertheless, we see M still part of the secondary collapse, not the primary collapse with the roof line. With that said, L is our primary member that's failing, that's buckling down, and I get that via through this failure of this member here, failure of that member there, right here, as it pulls down. Now this one could pull down also, and this one could drop down. When this drops down, this dropping down pulls on L, rattles it all the way up. Now, it's at the witnesses say a couple things. Witnesses hear the pool deck go down. They obviously able to clear out the building, and one witness even said he went out to here and looked and saw it down. It was edited video by the news, and so he has he talks about his apartment. He doesn't take a picture of that. He plays hero by the time he's done with his stories. Now he's silent on the whole subject. The mama bear runs down here. Oh yeah, thanks Charles for sharing that other video about the other lady wanting her mom to be called Mama Bear. All right, so her mom can be called Mama Bear too, but this is the true Mama Bear because she didn't just skedaddle. She went back for her family to say come now, robe and all, come now. So she's a true Mama Bear. Plus she went knocking on other doors, trying to tell them there's an earthquake. Get out of your houses. So she was truly stuck in Mama Bear protection mode. All right. Now, I don't know about her later stories or anything else, so I'm not up to speed on that. But that the first rendering was more clean along with her saying that leaving her son in the lobby to give her the phone number. She was already, she was acting in flight mode, but for some reason, the giving the phone number to the lobby lady was interesting. And he left though. He didn't. He said he never gave the what Tom educated me on. He never gave the phone number to the guard, the address to the guard. The guards never dispute it. Remember, sometimes I do videos to troll people to respond. Well, there's quite a few troll videos out here that no one's responding to, not just mine, but the other people conflicting each other. For example, he said they said that about the phone number thing, that she didn't know her address. She's not come forward and said I knew the address. She's not disputed that she didn't know the address or knew it. The news hasn't questioned her about that she not know or did not know, and they didn't ask about why she went back into the building and why was she down there, a lot of things. But let's move on from that and just stay with, stay with the witnesses that are solid. It would be this one, the lady who comes back, right? So she notices the garage go down. She's able to get into the hallway. That's very corridor, as they call it. That's very critical. That tells us that it didn't make it to the corridor at that point, this stage of the collapse. 412 is over here now. Now I've got to move. I keep moving around, right? Now the model lady's over here to the right as I looked again. She is to the right. She observes what she observes as a sinkhole reported to her husband. The lady, what do we have here? So she spent some time on the phone there because this person's able to observe, come back, grab her kids, and then exit the building, make it across the street. Some time takes place before his phone call takes place where the building collapses. So during that time, model lady makes a phone call to her husband and they discuss it. Would she have made it out? If she was running, I think she would have made it out. She'd have just not called the husband and ran. All right, that's the what ifs. And I saw the article, Charles, you sent me, and they did a lot of what ifs there. I don't believe in what ifs. The what ifs are amazing to think that. For example, I'm spending time doing this video. I go outside now and cross the street. I die. Well, a car hits me. If I didn't do the video, I would have never came in time with that car because things would have changed. The butterfly effect. We live in a butterfly effect, all right? We eat a hamburger today and then we like it. So then we eat another one tomorrow, the next, and the next. And supposedly you get cardiovascular disease from eating hamburgers. Well, the butterfly effect, your first hamburger you ate. It's too many what ifs. Come on, it's hindsight. But saying what ifs is using hindsight. And I think that's unfair to this situation. We need to go forward from here. What if they did the repairs? What if they cleared out the garage? Yes, that's critical. Now, that's critical to it. And those what ifs would go for the municipality. The municipalities, if they were more aggressive, but nobody wants a more aggressive municipality. Besides, this is that's the what if zone again. This is a back in time thing, 1980s. This is about retrofitting now. So forget what ifs. Now it's about retrofitting existing buildings and just moving forward. Okay, so now again, I would not have made it out of this structure. I would have stayed there evaluating and been dead. All right, so anybody says I'm being insensitive, well, I'm one of the dead ones. Okay, so I would not have just run out there. If I was outside, I would have backed off. I would have taken into consideration what could have fallen on me and backed off and observed. And maybe I would have thought, sinkhole also, being in Florida, at that time you got data thinking sinkholes. So, and then you'd have backed off and go, whoa, wait a minute, this thing can get big quick. And then you'd think, oh, wait a minute, it's by the ocean. It's only going to back up so much, but oh well, let's just back up towards, actually probably towards the ocean be one of the safest places. Not going to sinkhole the ocean, right? So let's go with the other ones. If the fifth floor, I think they slid down the debris, and then the ninth floor where they barely make it over out of the zones and make it out, and I think the father does not make it out. That's interesting because it was an immediate reaction from the collapse. So they did not feel, this is important to you for you to understand, they did not feel the vibe. They didn't have the timeline before because they said, there was collapsing and they ran out instantly and barely made it out. Well, we know that quite some moments went by before the collapse happened and before before this pool deck collapse happened and before the final building collapse. So the vibration of this collapse were pretty much felt, I'm theorizing, only by people along this plane here. This is G. This was C row right here, and this would be G row. All right, you call it lines if you like. I care less. So this is the G. All these are G's. Yes, one's turned different, and these are C's. But C here has a staggered deck. The load transfers out at this elevation. Remember, this is supposed to be 2'6". Now it's 1'6". That changes its ratio of strength, across the face of it in the span. Okay. This distance is approximately 20 feet. This is the front of the building. This is I, K, L, and M. This is a step down, as you recall. It's 1'6" step down. It's that drop slab detail. That detail that, there's that move like that. Oops, sorry. I'm taking some liberty there. So it does that move like that. And that's 1'6" here. And it's probably got a cold joint right about here, I'm guessing, because of what we saw under here. So they built it consistently that way, perhaps. And there's a column there, so you're going to make it over to a column. The question is, how did they get to how did they support it? Did they run this deck over top of the column fully and then put the transfer part, the step up and then over? That seems pretty logical to do it that way, but I just don't know. Okay, I could look for slab details. Yeah, I saw one with some rebar sticking out in the NIST documents, and it looks like two directional. Looks like a transfer slab, drop slab, but it could be a lot of places they did this around the entire structure. So I want to find one with a column detail. I can't find that one. If you guys can find that one with the drop slab detail and a column, so the column would be going up through it still. How did that column go through it? Was the column down here? And then it picked into the side of the column, or was the column on top, or was the column right there, and then the slab transferred through it? How was it? The drop detail shows like this, though, but it doesn't show how the column is anchoring. So these would have been heads sticking up, rebar sticking up from here. It doesn't quite show in the details of the drop slab details of this system. It shows like this. Look at my left mouse, my mouse by the left hand. It shows like that. But clearly there's a column through it. But there is no detail showing how do they do the columns there. So coming back to this little lady, that's an issue. So how do when we get the deck moving, how does it affect the drops? This deck moving here. This is only 1'6" now, no longer 2'6". No longer, it says varies, but no longer 2'6". It varies down here. It's now 1'6", and even smaller down here. But this is the secondary collapse, not the primary. So over here, how do we get this? Creates a shear plane because this is a staggered break right here, and the deck. Let's go like that. There's your construction joint. These create shear planes. Remember, you guys don't know it. I've been arguing with an engineer that calls me up and arguing, saying, no, I have these BMAs acting like a shear plane. I don't have it getting to the building that way. You got to go through these BMAs. They make a beautiful shear plane, even decelerating it, and then you still have the deck up here, the upper deck that it's got to reach up and grab from. So I just don't have, and you're coming through these. It's going to divide the deck up. So it's going to break it down into lower forces. Now we got this structure, this construction joint here that would also decelerate the amount of force it can apply on M. And so that's what my argument was with him, and we had that for some time. And his position, I believe, is still going through without explaining how it's getting past. He just won't accept that. But now, so now I have it where this is clear to me. It's more clear to me now with the video I presented with you. That this collapsing is between these two here, this BMA here and this one here. So let's do the BMA like that. That's that one. And I have it collapsing. It's staggered. It's an overlay. See, it overlays there. But now let's not overlay it. And so the main loading is this one BMA here. If you can get this BMA to fail, you'll get both of these to butterfly in. They fall inwards. So this one goes in, and that one goes in. This BMA here, and this one goes in. If you get this one in the middle to just drop down. So there it is. It just drops down. If it drops down, it pulls on both of these, shearing away from here, calling rotation. Not too much on M, but because we see this in the video that it's down. We don't see other BMAs switched in front of our way and pulled away to the side. It's a huge BMA. And we don't see it pulled over to the side in front of us. But we see this two-tiered system here in the image. It looks like part of the deck and possibly of the BMA on the floor, which would mean this one here took the rattle. This rattles up. This is the 7th floor. It rattles up, wakes the lady in bed, also I. So here's I and K. And there's L. She comes out, bedroom style, bedroom's here. Comes out over to there. But as this deck goes down, originally built by the parking garage, it pulls on, it tugs on here, it tugs on here, it tugs on this guy is the one that's going down, because this is where our planter box is. Our planter box goes down level. Planter box goes down pretty, can we get a green? Our planter box goes down pretty level. So that's telling me that this has gone down. This BMA has made its way down. This one here. That rotation takes place on the one out here. But so this is our L again. So this is why this is a slab. So you're looking at a slab detail 1'6" up in the air, 1'6" up in the air. And off of this pad, it's actually less. It's only like 7 inches off of the upper pad above this planter box. There's a 7-inch right there. And then he added more pavers on top of it, and it comes out to be like an inch and some change. After they added the pavers that they added out here, they also added up there. So it changes from a 7-inch step out to a much less step down by default. Here's our L again. So our L, again in the video, shows that that's our pulling. Now let's talk about these guys here, and let's go back to again, beam, columns. Okay, so here's column schedule. It's C and G is the important one. So here's C, and this is G. G's are, so let's confirm that for you. Calculator, 14 times 18 equals 252. 16 by 16 equals 256. All right, so the rebar is interesting. We need to see there's 4 number 8s in the rebar in the column. Oh, I'm sorry. Right here, here 6 C and G. There are 4 number 8s as you get above the 7th floor on the G. So you got to get to the 7th floor. You go to 4 number 8s. You transfer over. But on a C column, the face wall, you do that at the 6th floor, 1 floor below. So remember C and G. 1 floor below, you go to, on the 6th floor, you change it over to 4 by, on the front face columns, you go to 4 8s. They were 6s before. Before that, right below it on the 5th floor. 6th floor, you change over to 4 number 8s. And over here, on the next floor on G's, right behind there, you change it over to 4 number 8s then. So that's the 7th floor. So you see the stagger taking place there? It's got a built-in stagger that will help you with this tilting of the structure, if you will, as you see the roof structure. And that's via the rebar reinforcement. Further back, there's the G again. You have the 4 number 9s. There's the 4 number 8. So it's stronger than the one behind it. The G's column's behind it. So G is, so let's come back to that. We'll talk about, let's get the G, then I'll get you, right, there's G. See G? Now, interesting, there's I, and there's G. It's set, it has another set off. A 1 foot, it appears to be 1 foot or 10 inches set off between this one. That they set it back further. They say it's the same size as G here, but it's drawn differently. And that does matter because they have a scale here that shows these different sizes. But nevertheless, it's still titled as G, so we're going to say it's G, and it's just drawn, freehand like that. Look at G, look at C, here's C, here's C. This is where the building's sheared off. Right here's the plane of the wall. There's a column here, but there's no column at the end of the porch. And that's where the column, the wall, if you look at the videos, you see that it took off half the porch. There's no column there. A, B, C, D, E. I bet you that was going to be F. A, B, C, D, E, F, G, H, I. But they seem to shift over a few things. Here also, there's no column at the end of the cantilever porches. Over here, there are columns on each end of the cantilever porches. Over here are the columns on each end of the cantilever porches. In the front of the structure, columns on each section of the cantilever porch. On the back side, not. So the symmetry is not symmetrical, is it? There's an offset of 8 inches from this column to that one. Now we're back to that offset stuff again. So this one's definitely offset. There's no columns here. They ran the columns up, and they said, we don't need them anymore. This time we'll just bridge it over to the wall. We'll make it to the wall. I think that's an opening. We make it to the wall, but whoa, look at this span down the middle, our tributary area again. It's starting to get pretty darn big. Now, if this was a two-way slab, they're saying what? That these two, a two-way slab, so these are the boundaries of, these would be the columns of and the beams of the two-way slab. Well, then these clearly are, if these are the boundaries and these are the boundaries, clearly these are taking more load because their load is a larger area right here. But we didn't, theoretically a larger area like this, but in reality, these don't work in cantilever capacity. So this area is actually really going out to here like this. It's a heavily loaded area. And then the same with this one, not a cantilever, so it's pulling all the way over to here. I don't want to confuse you with that. That's a tough one. Let me leave that alone. But let's get back to this. This is where so H-I-J. So J might have been there. It might have been a column there. They just removed. Oh, wait a minute. There's J over here. They put J here. So H-I-J. Oh, J column is in the other structure. So to my man Tom out there, there's your J, Tom. No skipping. All right. So, but the point I'm making is that this should be a column here, like they columned it everywhere else at the end of the cantilever, because now this cantilever's got some weird action going on with it. And this is where I talk about it looks like it changed the hooks, a different pattern. All right, so there's your J. All right, let's go with G, back to G. So G is our level all the way up, and then there's the C face, and there's G, and we're in a different structure, so we'll leave that alone, right? And we'll go back to G and C, and this is M, right? I-K-L-M. M is the shear wall that everyone says doesn't exist. Well, obviously it worked. The problem is the rebar goes across the shear wall via the slabs into the slab next to it. This one worked because there was literally a wall here because the elevators built up, and so they couldn't go through the elevators. At some point they do go around, and the stairs are here. So, and then there's an open space here. So this wall system had J bars in them that pulled out of the top floor. I'm going to get to that in another video for you. Then you see again the new shear plane. It went around the corner a bit. Wait a minute. That one of them they cantilevered out, and then went around the corner a bit. And then is this the last one? Yeah, it sheared somewhere about here, which makes sense, right? The columns, and there's some floors that stick out a little bit. And this is gone. Half of it's gone. Half of the porch, half of this is gone, which makes sense, right? Because of the reinforcement ripping out because of the way they overlapped it. And that gave us that new shear plane. Okay. So what did I want to get back to the columns? So back to the concrete. The concrete, I'm looking to the right here. See if I can get to it faster. Column schedule. So now you saw C and now you saw G. And you see that C is the face, the one that initially took the bump from the deck collapsing. And it rattles, and remember Baltic connection, I said that in the beginning of the video, I believe, think of the concrete as the nut and the rebar as the bolt. Well, our bolt stays the same. Well, they get less, they get reduced, right? Instead of having 6 bolts going up, they change it down to 4 bolts. And the 4 bolts, they also change the nut at the A floor to be a smaller nut, a 4,000 psi. So the nut is a weaker nut, a weaker connection to hold the bolt together. The bolt connection is weaker now with 4,000 and only with 4 connections in it. And the next column back, the same thing. It's only got, and this is the columns. Don't get me confused. These are the columns that are weaker. The deck itself, where the bolts go into the deck, they go into the columns rather. Second floor framing right here. Let's go, well, that's the one to the right. Second and up. Okay, 4,000 psi up to 8th floor, 3,000 psi remainder. Do you see the difference there that's so weird? As in his notes, is that he says this 4,000, but then he says that the 8th floor switch over to 3,000. But on our column detail, he says go with our column detail. He says make the columns 4,000 psi. Remember we talked about that at intermixing, how the hell does he do all that? And you're allowed the percentage to intermix. But at the column detail, he says make that 4,000 right here. These are the columns. Run 4,000 all the way up. Okay, so we got supposedly a stronger grip force with that one going there. But then with the flooring, he says make it grip the bolt, if you will, with 3,000 psi. And that's set over here, that's basement, or second floor again, right? Second floor. Second floor. He says he says make those 3,000 psi, 8th floor and above. 8th floor and above, make that connection 3,000 psi. So they do that. And lo and behold, we get about an 8th floor failure as our buckling point. As the building was rattled, 8th floor on L is the size it can't, that's too much of a span. So you need to focus on L, and it's loading around the 8th floor, and its interaction. So 8th floor is 3,000 psi. It's 4,000 on the column, and so we are at the second floor and above, and we're going to go to I, K, L. This is L. Okay, so let's look at L's loading. All right, they on L, A floor, pretend like it's the A floor, we have only connections are three-sided on this column. Our span is 20 feet. Does this show it? And some change. So it would be like from here to here, 10 to 8. And it's on another detail. So in there are, and I talked about this in another video, our critical shear area is here. They used, and this is the tributary area. Okay, well they used 60. This is the one that comes down. So they used 6 5s on this side from center line, and on this side they used 8 5s. So this is the weaker side. Over here they use 6 5s, and the spans are they're about equal. 6 5s and 8 5s going this direction. So it's got a whole. This is with a pulling on this side. Incidentally, where the rebar crosses, it's going to pull on that side. It breaks the shear wall because they're slabs. There's only a mini shear wall here, and then this one here. But nevertheless, this is our L. And so L at the 8th floor has a connection of 3,000 psi here. So the building rattled, as we know it rattled. It shook. It breaks the connection there. That allows those floors to drop down. It allows these floors to drop down. So 8, 9, 11, 12, and this one is our penthouse. 8. And by chance, it looks like something's missing right there at the ceiling of 8. But there's the PSI right here. I believe it would be right about here is our PSI change on the floor that bought the connection, which allows, when it rattles the whole building, and everything's good to go up to there. Right there is where they change the 3,000 PSI. This connection of the rebar is at 3,000 PSI. The bolt is being held by a nut that's at 3,000 PSI or weaker, or whatever it may be. It's also in a cantilever fashion, so it's also got it, and it's only on 3 sides, and it's got to handle this cantilever. Now there's some negative load effects that I could probably do some deduction, but it would probably balance out against it because that would have a little flopping action going and a little more torque and more of a prying action away from it. If anything, these at that level, the vibration would, if anything, would want to help knock it down, in my opinion. So now they just got these hooks here going out to the slab. Well, the slab actually connects back to, so it's not connected to this column. These hooks are just hooks details to stop the deflection in the slab here. And they're actually connected back into this column here via transfer steel coming across, and then into this column times, I think there's 2 pieces of steel. They look something like this, perhaps. I think we did see a few images that look something pretty weak. It looks like, so there's a steel. It'll be 1, and oops. Yeah. And 2, and 3, and I'm going to guess that there's another one over here. So it's sort of like that. It's not very, I don't know this to be true. I saw where I saw 3 of them before, and that one that was leaning against the wall. I think I see 2 out and 1 off to the side a bit. And then again, we could add 2 there. You know what? Let's do that. Let's have a little fun. Let's add a secondary one there. It doesn't matter because they don't put it out much. It's not like it's there to there. They just horn the baby. It's not much at all. It's not much at all. I think this one is a little bit longer. So it's not much to hold this deck there once it starts rattling. It's only 3,000 psi concrete. It does that spalling action thing I talk about, where I show the lever action, where I say that it's holding the deck. In this case, the deck is going down. The rebar stays inside here for the most part, and it just pries off the top layer here. It doesn't appear to be 2 layers of steel that's really engaged beyond that into the all the way across over to here. It's over here, it is and overlapping, but we don't get there. We need to tie it into the columns. All this is just freestanding until you tie it into the columns, until you lock it in. That's why I talk about my ledger thing, my deck ledger repair. You bolt it in, and you make a bigger tributary at critical shear area. You can literally, with money, put steel all the way across here and start tying this thing all the way across from here to there to there, and make a whole new steel internal framing to the darn thing if you want to. There's a rule that says that I have that says if you can't hide something, celebrate it. So you could make it, something pretty artistic steel, right on the outside if you wanted to. Exoskeleton, like this is exterior. Now I'll give you a hint where I'm going to go with this. I'm going to go back to the 2000 reports, and we're going to look for what repairs were done. They call them stacks on the 8th floor, on the 9th floor, 10th floor, 11th floor. We're going to look at these floors again on the C repair, on the C stack. I think it's called the C stack. We're going to look at those repairs and see what we can find, and see if there's an inherent weakness from the repairs back in 2000 when they did this structure. So that's very critical to this failure, perhaps, I'm showing this as a just non-repaired state, that this was just original. But we know that repairs took place in 2000, that they were all over this place doing repairs. How much did they go into, let's say, the 8th floor? How much inherently weak did that develop? Did that become at the 8th floor? And to do that, I think we could also probably look at the current report on what he was going to repair, because he was going into, wasn't he going into the structure also? I'm playing stupid. Wasn't he going into the structure also to do repairs? Giving you guys something to think about and go look for. So let's get rid of that. So now I think I've got you up to speed now to help you understand that we only got 3 sides of a critical shear area to support a large 20-foot span, and then there's a greater span there. You know what? I think there's a measurement one. Right there. There's 22 feet right here. There's 22 feet. There is 22 feet, and this would be 22. This one here is 22 and some change. All right, there is from IKLM. I can't help it. Look, there's 141 feet between here and here. I couldn't help it. So there's 22 feet, 6 inches. So that's the largest span between our M. There's our M and our L. So our largest span, but it also has 21.6 over here. So L is the center span between these two. It's the center reinforcement between K and M. Total of 44 feet. 44 feet. So if it goes, it's got 44 feet. Great, didn't mean that. If it goes, it's got 44 feet. From here to here, let's do it like this. It's the same as there to there. Okay, it's got 44 feet. Just a deflection of it to go. It's going to do that. Now you see me having it pinned here, not moving. In reality, this is cross steel over here. So when this goes down a bit, it starts tugging on past M, and we see that little teardrop, the teardrop forming over here when it starts tugging. it starts tugging on those floors. You can determine where, when you see the deformation, which part it's tugging on, and that's our beginning floor. Let's go back to the video. Click. So right now, it looks pretty good. So it's more to the left that is failing. But now we see deformation. There's a tug there. I see this opening up. I see this floor being tugged down. So there's our 8th floor, 9, 10, 11, 12, penthouse. There's our 8th floor. There's our PSI again. So it only had to go up to the 8th floor, which would show the debris in the other camera. Remember, the steel goes across here. That's our tugging effect. But M is still standing pretty good, even though it's tugging across it to some degree, some steel. But why M stands so good is it's not much. It's only connected across the face here. It's not the backside of this connected to it. There's nothing on the backside. The steel comes back, it rotates, and it's here. So it gets to, it's not much engagement as you may think. Oh, wait a minute. Let's do this. Let's get rid of that. Good. So I, K, L, M. Here's M. So there's not much engagement there. There's this rebar here, and you see that rebar comes this direction. This one goes this direction. So 6 number 5s. But you can see it doesn't go into, it's sort of, I don't know if it stops at the plane of the building or not. It doesn't hook in there at all. These are hooks. It doesn't show it hooking inside the columns. So that's a hook that way. That's outside there. This hooks this way. It's actually not showing how the column is interacting with the deck. Maybe these 8.5s go across it, and that's our ears, and the center line is, as I keep saying, I think I found 13 inches, something weird. 13-inch rule. Let's see if it's down here. For reinforcement at cantilevers at 4-inch, 13-inch on top, centers on top. Okay, yeah, that's the 13-inch on center. That's the cantilever. Okay. Temperature reinforcement steel at cantilever. All right, that's temperature same. So it's 6 and 8 appear to be the same note. I don't think they have 2 pieces of bar together. Do not construct masonry units. Right. We talked about the masonry units. Oh, masonry units. That wall. So K, L, and M. And I point out that extra wall in the middle there. The column, rather. This one here. This one there. There's a wall, the party wall between these guys that for between K and L for the not a party wall, a wall, partition wall for the bedrooms, and that's probably a decorative way so you can take, butt it up against something. It's still transfer. It's still a nice indicator of what's going on these floors at this point, of what's falling more so than not. There's an internal failure on the back side of it. G is pulling down. It broke away from G at that point, I believe. All right, going back to I, K, L, M. So as we watch over here, this is disengaging, and some of it's ripping out, some of it's tugging, and a lot of it finally breaks free as it makes its way probably over to this shear wall here. It probably does pretty good for a moment there before, as I talked about in the previous video, it takes out the H-beam at the bottom, and the building tilts forward, and it collapses from the bottom up. This is from the top down, 8th floor and top floor down. This is from the bottom floor up. With some failure in the floors up, the interaction across here. but mostly you can see it's already sheared apart from the roof line. The roof line is sheared apart, and there it is there, which is very telling in itself, saying that L has already failed and has significantly dropped down into the garage area. Oh, the flapping. How you see it flap so easily down the rotation there. We have a break from here to here is a corridor. You see there's the span of the concrete. As this goes, it's going to make an easy flap. And then the puncturing happens there, or buckling happens to the internal columns. And we make it back to right about, somewhere about here is our rotation. This might be our rotation point that we're looking at already, or it might be right about here of the rotation point inside the video. Inside the video there. This is our M, as you can see, and that's the main structure here. As you look at the top of it, there's that porch area, the cantilever porches I talk about, and that's going to be up to your roof line. And then you have that center. So right about here is the this section right here. So this is our separating, right? This is our separation. To get that separation, I have L as this shows the most deflection, most movement, buckling. So there's this one being a rattle per the video. We get this one failing, we get everything pulling towards it as its unsupported spans are so great. That's where we're at. We're at the huge spans, the 40-something feet. Huge span once you take out L. Oh, there. Okay. So I, K, L, M. There's that block wall right here. We see the block wall, block column, and there's the wall I'm talking about. It's the one time just shut me down on my fun move. But nevertheless, it's still load bearing. I think that extra load of that block wall is not for free, but it's going to be a very good indicator of what's going on between the span there, because you're able to observe when it finally moves. You're able to observe when it finally buckles and at what floor level it buckles at, which is somewhere about here. So it's telling you that these floors are still flat until you see the buckling. And they behave differently. As you can see, the buckle happened with a segment still in place, and then a buckle happened between it. So they behave differently construction-wise. The joint was able to stay together, just so you know. So there's that. This is this.